Okay. I think we should get started. Thank you all for coming. Good afternoon. Probably don't have to introduce myself, but in any case, I'm Luis Plana, the leader of the microarchitecture design and implementation group known as the MAD group. We're all MAD, and it helps do the job. We're very excited today to have Reza Ismaili talking to us. Reza is a senior research engineer in my group, working specifically on the VPU activity. So he's very interested in acceleration of computation. In particular, he's been looking at energy efficiency and energy efficient implementation of microarchitectures for computation. I think he'll be presenting today some of his latest work done in conjunction with all those people listed in the slide. And I think some of this work was presented very recently in Micro 2025. So this is already very good work. Please, people in Zoom land, write your questions in the chat so that I can read them after the talk. People in the room will allow them to ask the questions directly. Okay. Then over to you, Reza. Thank you.
Yeah, thank you, Luis, for your kind intro. And good afternoon, everybody in Zoom and people in SC. So today I will be presenting our work empowering vector architecture for machine learning, the CAMP architecture for matrix multiplication. As Luis said, this work was done in collaboration with my colleague in BSc. Okay, let's see if not freeze the page. I don't know. I cannot go to the second slide. Okay, only the mouse. Okay, sorry. Let me start with a quick overview about this work. First, I will give some background about the growing gap between quantized machine learning workload and VPUs. Then I will start to talk about the VPUs and having some background about the VPU and see how the high performance libraries implement the matrix multiplication for machine learning application. Then I will explain why VPU cannot fully exploit the quantized data for small bit width applications. And then I will talk about the CAMP architecture and how our proposed architecture can address this limitation. And finally, we have the experimental result and performance gains. Okay. In recent year, we know that AI and machine learning have a really good progress. We start with a simple pattern recognition or like simple digit recognition, and now we are in the prompt-based application and it's everywhere. So we are trying to do everything with the prompt, with really sophisticated chatbots, but these come with some kind of exploiting the growing demand for the memory and computation resources. So to address this limitation, we have like different approaches in the hardware side and also in the software side. And they grow up some, let's say, in some kind of parallel way. In the hardware support, we have fast methods, but specialized methods like ASICs, TPUs, GPUs, you name it. And also we have the general purpose architecture like CPUs and VPUs, which they are everywhere in the data centers, in your laptops, but they never have developed by having the AI workload in mind. So by checking also the software side, in software side also there's different techniques to compress the data, like sparsifying or quantization. Sparsifying is like pruning the networks or making some elements in the network zero to compress the data, or let's say reduce the memory footprint. Similarly, quantization is just like changing the data type from, let's say, this 32-bit or 64-bit floating point to small bits, even to 1-bit operations. But because these two methods are evolving in two parallel ways, we have a growing software and hardware gap between them. Especially, we are focused here on quantization and the general purpose application. We know that, as I said, quantization minimizes the data bit width, but on the other side, CPUs and VPUs always are based on the floating points. So, for example, if we want to see this with a specific example, for the ARM architecture, ARM SV architecture, if we support FP32 or let's say floating point with X performance, we cannot obtain any increase in the performance for the int 8-bit and int 4-bit. Even they cannot support 8-bit operation or 4-bit operation. They solve this issue in the SME architecture ARM v9, but the obtained speed up is really limited. It's 2x. Theoretically, we expect to have like 4x speed up when we, let's say, move from 32-bit to the 8-bit, but the obtained speed up is only 2x, right? So this is kind of our motivation. We in the software side, we push the limit of the data to small bit, like 2-bit, but in the hardware side, we don't have proper, let's say, hardware to let's say, support these data types. This is exactly where camps or architecture come into play to fill this gap between the hardware and software. And thanks to this architectural innovation, as you can see here, by using the camp architecture, we expect speed up even much more than the data type change. For example, by moving data type from floating point 32 to 8-bit integer, theoretically we should obtain 4x, but as you can see here, the speed up is around 7x. And I will explain the reason behind this speed up. Okay, but first of all, about the VPUs, and let's have kind of background about the VPUs. Unlike to this scalar units, SIMD or single instruction multiple data, they execute the same instruction on multiple data elements. And the vector processor is more generalized form than the SIMD, which are variable in the length vectors. So backing to the matrix multiplication, not backing, starting with the matrix multiplication. We know that the matrix multiplication is the cornerstone for the many operation for the AI, especially for the AI application. The naive method is just like using inner product operation. We know that we choose one row from the first matrix and one column from the second matrix, and inner product of these elements will give us the output of the corresponding element. But this is not cache friendly, as you can see. And the reason is that in a realistic scenario, this matrix is really large, and we cannot fit this matrix in the different level of the cache. For example, just imagine you want to bring the row and column from the cache, and the matrix like 100 or even more than 100. You cannot fit this even simple row or column to the cache. So what is the solution? And why this is not cache friendly? We start with a really simple experiment and see that the matmul, or let's say the naive matrix multiplication, cache miss rate is really high. As you can see here from this number, which is down on the ARM Fugaku core, by using the simple matmul operation, or let's say the naive operation, the cache miss rate is around 40%. But by using some, let's say, more smart algorithm like ULM BLAS algorithm or GoTo BLAS algorithm, this cache miss rate can reduce to a really small number, under 5%, let's say. Let's see how this method works, because before designing any hardware, we should know what is the best software solution and how we should solve the optimization problem for different softwares. I mean, in terms of hardware. So BLAST library, unlike the naive methods, slides matrix in different parts. And by tiling the input matrix and the output matrix in different blocks, we can fit these matrices in different level of the cache hierarchy. As you can see here, for example, by splitting output matrix and the second matrix into large columns, we can fit this matrix in the level 3 cache. Similarly, the for loop around our microkernel can partition second matrix and the output matrix into panels to feed again to smaller matrix in the level 3 cache. Similarly, in the first and the second loop around matrix, around the microkernel, we can partition the matrices in different level of cache. For example, as you can see here, in the second loop around microkernel, we have different tiles of the input matrices. We have as you can see here, we have different elements here, and by setting these parameters like NR, BP, KC, actually you can adjust this method based on your hardware, based on your architecture. Depending on your architecture, you should play with these numbers to have the best, let's say, throughput for your hardware. Zooming into the microkernel of these methods, we can obtain that, unlike to the naive method, which we select the one row from the first matrix and one column from the second matrix, this time we choose one row from first matrix, sorry, one column from first matrix and one row from the second matrix. As you can see here, by obtaining all the outer product results, we can have all the necessary multiplication operation. For example, if I select A0 to A3, and in the second matrix B0 to B3, and obtain the outer product means that you should multiply all the elements in the first vector with all elements in the second vectors. So I choose only column and row from two matrices, and as you can see here with the pink color, I would obtain all the required results. Same thing for the other rows and columns. Just we select the column and the row from the second matrix, obtain all the necessary multiplication, and we will go to the other row and column. Even with this small picture, you can understand why this method is much more cache friendly compared to the inner product. Because with inner product, when you choose the first row, you still need to go through the columns, and if you go one step more to the next row, you need to back again and load the same numbers into the registers. But with this method, when we read the numbers, we will pass that the numbers, and we don't need that numbers anymore. Let's see why VPU fails to efficiently execute this go-to-class algorithm. Until now, we see that how the software works and how we should do the elements, but we have some problem on the VPU side. Let's see what is this problem. We said that we need two columns from the first matrix and row from the second matrix. Let's load them into the two registers, but we have a problem. We need outer products, but the VPUs only can operate in the corresponding element. I mean, you can only have the multiplication between A0 and B0. In the VPUs, you cannot have multiplication of A0 and B1. For doing this one in the software, the only solution is just duplicating the second register in different registers, in different, let's say, vector register. For example, we can duplicate B0 along register 2, same for B2 and B3. By using this method, for example, by just multiplying first register with second register, you can obtain all the corresponding element between A0 and the second column. But this method is not also, let's say, smart method, because we need a lot of duplication operation. We need a lot of, let's say, vector register, and we know that the architectural vector register is limited. So also we would have some kind of challenge in the about the overflow. because multiplying 8 bit with 8 bit would result in 16 bits, but the register is limited to 8 bit for one element. So even if we manage all of this, let's say extra instruction and extra register, do we have still enough functional unit to perform this operation? The reason is no. As you can see here, according to experimental result, by using two different high-performance library like ULM-BLAS and GEMLOP, we can see that the functional unit busy rate is too high, even more than 90%. It shows that by using this method, the high-performance library, the functional units always are busy. And it shows that unlike to the floating point, for the integer units, the problem is not memory bound, it is compute bound, when we need more functional unit here. Okay, the remedy for this problem is CAMP. Let's see CAMP how deal with this inefficiency for the VPUs. Again, we are loading columns and row to different vector register. And CAMP idea is just, why not supporting outer products? Let's support this outer product for all the elements in the register. So by using this method, we somehow can generate all the required multiplication. And as an example, you can imagine these two matrix multiplication with the architecture which has 2 lanes, and let's consider that each lane have 8 elements. So 2 lanes, 8 elements means 16 elements in total. For example, for matrix A, we can load A0 to A7 in the first lane and A8 to A15 in the second lane, right? So, and we know that CAMP architecture can support the outer product. So just by loading these numbers to 2 different vector registers, we can obtain all the required multiplier, right? But still here, we need some kind of accumulator, some accumulator between the numbers in the lanes and also outside of the lane. We can call it intra-lane and inter-lane. As you can see here, for example, in lane 0, we multiply A0 by B0 here. And also, we need to accumulate that one with the result of A4 and B4. And the yellow one here is the intra-lane accumulator. But we still need this number with the obtained result from the second lane, and we call it intra-lane accumulator, inter-lane accumulator. This is the idea of the CAMP, equipping VPUs with some outer product and also intra-lane and inter-lane accumulator. But we need to be careful about the outer product operation. We know that for the VPUs, we always want to support different bit and different bit width, right? For example, we need to support 4-bit, 8-bit, 16 bits. But by using, but if we want to support the outer product, we need to be careful. For example, just imagine same architecture. This time, the whole vector length is 4n. It means that we have 2 lanes, which each lane is 2n bit. If we want to operate the outer product between them, we need 4 units of 2n bit multiplier, right? Because we need to multiply the first element of the register 1 with first element of the register 2, same with the second register, same story for the second element of the register 1. So in total, we need 4 units of 2n bit multiplier. Let's halve the data bit width. If we make it n bit, then in this case, we need 16 units of n bit multiplier. And it shows that halving the bit width will result to 4x more multiplier units. It shows that we need a bunch of multiplier, and we should have some kind of solution for this architecture. We use the divide and conquer method or algorithm for this architecture. how this works. Let's see it with with an example. The main idea is just by splitting the inputs, operands, we can obtain the multiplication operation with small bit links. For example, here, let's imagine the input bit width is 32-bit. By using 4 16-bit multiplier, an accumulator, and shifter, we can obtain the 32-bit multiplier. Again, we have one 32-bit multiplier, which is based on the 4 16-bit multiplier. Let's go one step more, and again, do the same philosophy for the 16-bit. Then this time, by using 4 of 8-bit multiplier, we can obtain 16-bit multiplier. So in total, we have 16 8-bit multiplier, which is able to do the 16-bit multiplier, 4 16-bit multiplier, and also one 32-bit multiplier. Going this one more step with results to a 4-bit multiplier. So in general, we have like 16 4-bit multiplier can support different bit links. So, and we see that this is the exactly same scale which we had for the VPU units. So we choose this architecture as a, let's say, building block of our multipliers, or let's say the motivation behind our multiplier. Now we need to have our architecture, right? So we equipped every lane with one camp architecture. Means that, for example, this figure is for the ARM SV architecture, which we have 8 different lanes, and inside of each lanes we have ALUs. So we add our camp architecture to let's say facilitate this matrix multiplication in the ALUs. And we know that we show that the camp architecture is the combine of the multipliers and accumulators. So still we need some inter-lane and intra-lane accumulator between this multiplier. It means that we should be careful about which number we need to accumulate. In this case, we need, for example, to the corresponding element, first element from each lane should be accumulated with each other, and second element should be accumulated with each other, and the same pattern for all elements. Also, we have one extra auxiliary register in this architecture to avoid frequent store and load operation to the main vector register or memory. This is our proposed camp architecture. Now let's, and we should remember that by adding this support to the VPU, it seems that we still support different bit lengths multiplier, but also we have like some kind of, let's say, extra feature which can multiply 8-bit multiplier and also 4-bit matmul operation, matrix multiplication, let's say. Back into our go-to-blast algorithm, we need to see how we should integrate this multiplier into the go-to-blast algorithm. In the left side, we have the software method, which is based on the outer product. And in the right side, we have our proposed camp architecture, which it takes the corresponding matrix from the first operand and second matrix operand and generate the output results. For this case and for this architecture, camp support 4 by 16 8-bit multiplier multiplied by 16 by 4 8-bit multiplier, which results in 4 by 4 8-bit multiplier. So we send these tiles, this matrix, let's say, packs to the camp. We multiply them, store them in the auxiliary register, and finally we can read this final register from our auxiliary register. And we avoid a lot of store and load to the main memory by using these auxiliary registers. So let's see what is our methodology and to evaluate this setup. We use Gen 5 and also the hardware synthesize to evaluate our method. Also, we experiment, and also we check 2 different architecture, ARM SV and also the Sargantana RISC-V core, which is from BSC. For the ARM SV, we use the simulated Gen 5 full system simulation, And also we have the bare metal simulation for the Sargantana one. For hardware synthesis, we synthesize both architecture in 7 nanometer and 22 nanometer to have a fair comparison because Sargantana, the baseline Sargantana core technology is 22 nanometer, and also for the ARM SV is 7 nanometer. So here we have like fair comparison between the ORCamp and also the baseline. For the benchmark, we use different LLMs and CNNs to see the performance of the camp. And also we use the high performance libraries to have a good support in the software side. According to the synthesis results, as you can see here, we have like 1% area overhead for the camp compared to the Fugaku core. And also for the Sargantana case, we have like 4% area overhead. Okay, we add like 1% and 4% area overhead. Let's see how much speed up we can obtain by using this camp architecture. Comparing to the baseline, which is a 32-bit, camp can reach to 17x speed up for 4-bit integer and 10x speed up for 8-bit integer by using different high-performance library and for different networks. For example, here, as you can see for the AlexNet, we can reach to like 17x speed up compared to the baseline. Baseline here is the OpenBlast. Remember that OpenBlast is really aggressive, high-performance library. So same for the other library like GemLopi, which is developed by the Google for small integers. And also comparing to the different LLM models, as you can see, again, CAMP also shows really good performance for different LLMs. We should consider also one important thing. We need to note that just by changing the data type here, and we, you know, the gray case here, and v int 8 is a data type change speed up. I mean, we don't change any, this case doesn't have any hardware support. It's just pure software method. It means that in ARM SVE, if you go from 32-bit to 4-bit, the maximum speed up you can obtain is 3.5 bits. But by using the CAMP one, you can reach speed up like around 8x. It shows that CAMP architecture is not just simple data type conversion. And we can say that the 4.5x of the speed up is come from the CAMP architecture. And yeah, the same. Also, our results shows that, for example, for the CAMP instruction count compared to the normal methods, normal library instruction count, CAMP instruction count is around like 10% of the normal high performance library. And this one shows the reason behind the speed up of the CAMP. By using the CAMP, the number of instruction remarkably reduced around 10% of the normal cases. Same case for the CNNs and also for the LLMs. As a conclusion, CAMP can operate as a standard integer multiplier or as a matrix multiplier, follow the structure of the high-performance BLAST library, like PhotoBLAST algorithm or this, execute quantized gem directly inside the BPU lines, and also support low-precision data type, 8-bit and 4-bit. Depend on the designer, it can also reduce to even 1-bit. And also, as we show from the results, it can have a speed up around 17 speed up and around 80% energy reduction compared to optimized software libraries. Yeah, thank you for listening, and glad if.
Should we thank the speaker? Okay, and we can open now the field to questions, both remote and present. Um, um, I suppose we can open the mics if you want Jonathan to ask the question directly, because there's not a. I thought there might be.
Yeah, sure. Hello, thank you, Reza, for the presentation. Great work. I have a short doubt. Have you thought about RISC-V BME and how you could feed camp with RISC-V BME? I think that they are quite compatible in the approach. So have you considered that?
Yeah, thank you, Jonathan. Yes, actually, we are considering to also include it, but we start from the now we start from the supporting floating point. Yeah, in the next step, that's our second target, Jonathan.
Okay, and then oh, you mentioned floating point. So this is pure integer, right? Then
yeah, this is pure integer.
Oh, okay, okay, great. So so my next question derived from the first part of floating point. Do you think that the divide and conquer approach will reach some limit in terms of latency, in terms of hardware implementation? I mean, on the side of the physical design part.
Okay, for that part, actually, depend on your pipeline and depend on your stage, you can meet this time requirement. So, for example, in our case, our targeted was like around 1 gigahertz and 2 gigahertz for the ARM SV, and depend on your stage, you can easily meet this latency. But in terms of the area, yeah, this could be, yeah, you are right. This could be more huge compared to the normal multiplier. But the reason behind is by using this structure, you can support different bit lengths with the same architecture.
Yeah. I totally see it. Very nice. Thank you. That's the questions that I have.
Thank you.
John?
You mean in the experiment? Actually, we don't have a compare between the RISC-V and you mean in the motivation part, right? Here. Both are based on R. The next one. Okay. Yeah, this one is RISC Sargantana with CAM support. Yeah, it's just like, yeah, exactly. Using CAMP in the SV, we would reach to 7.4x speed up, and the RISC-V is like 2 times more speed up. I can say that because we use this high performance library, and I think that comes from the baseline library, because for the RMSV we have really aggressive library for the matrix multiplication, but for the RISC-V maybe that's not much. I mean, compared to the RMSV, they are not good like we have for the RMSV. Yeah, exactly. For the RISC-V, yeah. Thank you. Yes. Sure.
If you can repeat the question,
Yes.
yes. Yeah.
Pavel have question regarding the divide and conquer architecture here. Mm. 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 Thanks, Paul. I think the main question is just like about the adder which we use or about the multiplier we use in this architecture for the divide and conquer method. At the moment, yeah, you're right. Maybe because we are scaling down to 4-bit, and that means we only have some kind of accumulator there. And as you said, the bottleneck for the accumulator is carry save adders. So maybe having more in an algorithmic level, let's say more smart idea will be help us to reduce this critical path. But at the moment, the method which I use, I just wrote them and give them to the cadence and said, okay, you have this constraint and go find what is the very best with this architecture. But maybe using the algorithmic level, yeah, we can deep into that algorithms to check if we can find any better solution rather than the, let's say, the cadence methods, synthesizer methods.
Don't know.
Yeah. For myself, maybe I'm not good. Maybe the programmer, I never can defect this cadence until now. So I was always just having something in my mind. Cadence always just giving the simple, even let's say you tell cadence, okay, just simple 8-bit multiplier, A star B, give me with this constraint, always come up with you with really good solutions. And let's say in terms of anything you consider latency and power, better than just writing your from scratch. So that's why I never go to that direction, but it could be, yeah, thank you. Yeah, it can be really good. let's say, research topic for that part. Because as you said, everything is just repeating, and we can replicate many algorithms, sorry, many hardware here to obtain the final results. Yeah.
Any other questions? Naive question. So how does a very sparse matrix affects this architecture? If it's not dense, if it has loads and loads of cereals.
Okay, this question always comes from the reviewers, right? Okay, everybody like the sparse matrix. So how about the sparse matrix? Actually, at the moment, we don't have that kind of support for the sparse matrix. And in the camp architecture, the only benefit of the sparse would be memory footprint. So in terms of hardware, we don't have support for the sparse matrix yet. So maybe just by changing the type of the data, that could be useful. But at the moment, we don't have any specific support for the sparsity. But that one's also another interesting things to check. Yeah, sparsity.
Yeah, even teaching this in an AI world where a lot of matrices end up being very, very sparse, right? But that's something to think about. Also, there are many different ways of storing the matrix in memory formats. Does this have an impact on camp?
You mean like different way in terms of the database?
The way the matrix is done, row major, column major.
Okay, yeah.
The normal.
The story behind the camp is just like we start with the high performance library. We start with checking all the libraries in the literature, and we ended up to the BLAST library, go to BLAST algorithm, and we check, okay, this one is saving the row measure, for example, for the first matrix, column measure in the second matrix. So our hardware should be in this way, not any other way. And we should store exactly with how the software do. But as you said, if the library changes, let's say we find a better solution for the matrix multiplication, which change the style of the store, it doesn't matter. Camp not this camp, but some small modification inside the camp, we can support